Okay, so let's talk about some different properties, some different physical properties more specifically that are affected by intermolecular forces. One of them is viscosity. So, viscosity is just the resistance of a liquid to flow. And so, if you think about when a liquid flows, a liquid is composed of molecules, right? So, flowing is just molecules just gliding across, passing one another. So, you can kind of see how intermolecular forces are really important. If intermolecular forces are very strong between different molecules, then that material will feel resistance against molecules moving past one another. So typically, like I say here, viscosity increases with increasing strength of intermolecular forces. So when we say something is really viscous, such as honey, it usually has a lot of resistance of flowing, so it flows quite slowly. And so, like in our honey case, since viscosity is very high, we can predict that intermolecular forces in honey is very high. All right. And so viscosity increases with increased presence of intermolecular forces, but viscosity also decreases at higher temperatures. And so, like our honey case, if we wanted to get honey to flow, I was actually making granola the other day, and I wanted to put honey in it and get it to mix around with my oats. And to get the honey to flow enough to get it to mix, I actually microwaved, my container of honey for like 30 seconds. And then once I popped it out and the honey was hot, the liquid, the honey was able to flow enough where I could just dump it into my granola and mix it around much more easily. And so here, we say that at higher temperature, viscosity decreases. Am I spelling that right? Yeah, will decrease at a higher temperature. So that is clearly exemplified in my microwaving honey example for granola. And the reasoning here, at higher temperature, there's more available kinetic energy to overcome intermolecular forces versus if the honey was really cold, right? Like not frozen, but like cold. Like maybe my house is like 60 degrees Fahrenheit because I don't turn on the heat or something. Then that honey will not have as much kinetic energy available for molecules to flow past one another. Versus if I warmed the honey up to like 100 degrees Fahrenheit or something, just kind of like hot water temperature, then the honey will flow a lot more easily because there's available kinetic energy to overcome intermolecular forces. All right, and so here are just some examples of a series of hydrocarbons and different viscosities. So you can see we have it's a bunch of hydrocarbons, and essentially where we get heavier as we go down. So since all of these hydrocarbons are nonpolar, only London dispersion forces are present. So if molecular weight increases going down this series, then our London dispersion forces also increases. And so since that's the only available intermolecular force, the total intermolecular force increases down this series. So IMF increases. And so you can see if we look at the viscosities for all of these corresponding substances, as we get heavier, as IMFs increase, we see viscosity increases. You can see that we actually moved the decimal place here, one less. So decane actually has the most viscosity. All right. Okay, so another type of property that is affected by intermolecular force is surface tension. So we interact with surface tension a lot with the different liquids that we work with every day, such as water. So, what surface tension is just the net downward force experienced by molecules at the surface of a liquid. So, surface chemistry is different than bulk chemistry. And the reasoning there is because in a sample, if you just look at the bulk, like in the middle of the sample, you can see like this atom has atoms all around it, 360 degrees around it. It's kind of in the same environment. Every single cardinal direction is looks somewhat the same, right? That would be like if you were sitting in a crowd of people and you were in the very middle. It doesn't matter which direction you look, north, east, west, south, it all just kind of looks the same. It's just a crowd of people that way, crowd of people this way, crowd of people that way, crowd of people behind you. Right? It all kind of looks the same. But what's different at the surface in terms of intermolecular forces, right, is that at the surface, you look one way, there's some atoms that way that you can interact with. There's some atoms this way that you can interact with. There's some atoms below you that you can interact with. But above you, there are no atoms. So there are no intermolecular forces available for you to interact with above at the surface. And so that is where surface tension comes from. It's this net downward force experienced by molecules at the surface, because this molecule right here is attracted towards this molecule, this molecule, this molecule, this molecule, if there's like some type of intermolecular force available. So this molecule feels a net downward push in this direction, right? Because there's no counterbalancing upward force to cancel it out because it's at the surface, right? Versus if you look at this molecule, there's a molecule, another molecule, a neighboring molecule, and intermolecular forces all around it. So all of those net attractions cancel out, right? And so, yeah, what else does this say? The molecule at the surface experiences fewer attractive interactions than those in the bulk. So since there's this net downward force on the surface, most liquids will seek to minimize the surface area. All right, so that's why water forms droplets. All right, so liquids form spherical droplets because they want to minimize their surface area. All right, and so a sphere will give you the smallest surface area possible. And so typically when we have high intermolecular forces in a sample, you will also see high surface tensions. All right, and so if there's a high surface tension, you will be able to, essentially this force, downward force, is stronger. All right. Okay. So a way you could test this out, actually we were going to do this in lab, but because of going digital, we're unable to do this in lab, but you can do this at home. So if you have a dropper, so get a sample of water and see how many drops of water you can get onto a dry penny. So like put the penny down like this way, right? And then count how many drops of water you can get onto the penny. All right, it'll be some high number. I don't know, like 40 or something, before the surface tension breaks and water goes everywhere. You'll get about 40 drops. So then do the same experiment, but add a drop of soap into the water. So soap is an ionic compound, and what it does is actually break the surface tension of water. So when you do the drop experiment again, because now you've lowered the intermolecular forces. Essentially, you've lowered the extent of hydrogen bonding available in water. So you've lowered the total intermolecular force in your soapy water solution. So then try the experiment again. So dry off the penny, do it again, and you'll see that you'll only get like, I don't know, like 20 drops of water before, of 20 drops of your soapy water before the surface tension breaks. And that's because the soap lowers hydrogen bonding and total intermolecular forces available in water. Okay, so that is surface tension. All right. So another property that we can look at relating to intermolecular forces, which is pretty important, is vapor pressure. Vapor pressure of liquids. So vapor pressure is defined by the vapor that's in dynamic equilibrium with a liquid sample. You will go into more detail about this in 1220. When you talk about equilibrium, you'll talk about equilibrium in 1220. But just so you know, that vapor pressure is caused by, all liquids have vapor pressure. In a liquid sample, you will have some amount of vapor above the liquid surface. So if you have your cup of water, right? This is a liquid. There are some gas particles of that same sample above the liquid. Always. Always. So vapor pressure. The amount of gas or vapor pressure above a liquid is defined by its temperature and by its intermolecular forces. So if you have a glass of water sitting at 40 degrees Fahrenheit, like if you have it outside on a cold day, the vapor pressure above that water would be different than if you had that water inside where it was 70 degrees Celsius, in like room temperature. All right. And so the consequence of vapor pressure, I think, maybe I have an example, but evidence of vapor pressure is if you have a glass of water out and you leave it out there long enough, eventually it will all evaporate and disappear, even at room temperature. So you never actually boil the water off. If you just leave it there long enough, it will all evaporate and disappear. And that's because at any given temperature, some molecules in a liquid have enough energy to overcome intermolecular forces and break free of the vapor phase. And that's due to a Boltzmann-like distribution, or Maxwell, remember Maxwell Boltzmann distribution curve? Boltzmann distribution. So some molecules will have, kinetic energy, some average type kinetic energy, and some have slightly more kinetic energy than other molecules. So at a certain temperature, some of those liquid molecules will have enough energy to break through to become a gas. So that's what this is basically. So here's an example of the graph. So essentially at a lower temperature, our Maxwell-Boltzmann distribution, just like for our gases from chapter 9, is a bit narrower and a bit, oh, this should say kinetic energy. Sorry. Kinetic, here. Okay. Okay, this should say kinetic energy. All right. So at a lower temperature, the average, the most likely kinetic energy of a molecule will be somewhere around, around here. But at a higher temperature, that will move slightly over. That more molecules will have more kinetic energy. And you can see the tail end of our Boltzmann distribution. Now more molecules are able to break free. So if you do the, leave a glass out experiment, leave one glass out, at room temperature, leave one outside that's at 60 degrees, or sorry, like lower 40 degrees Celsius. In theory, it would take a shorter amount of time for all the water in our room temperature glass to evaporate and compared to our colder environment glass of water to break free. All right, and so yeah, at a higher temperature, there's a larger fraction of molecules to have enough energy to break free. It increases. Okay, let's keep going. All right, so how else can we think about vapor pressure? Typically in chemistry, when we're working with gases, we're not working with open containers, like my glass of water example. That glass of water is open to the atmosphere, which is essentially infinite compared to that glass of water. So that's considered an open system. So yeah, so in an open system, a liquid will eventually evaporate. But in chemistry, typically we talk about closed containers. So this is what we have here. So I have a sample. This kind of looks confusing, but it's not really. Let's see. So this is a sample of ethanol. So when I introduce ethanol to this evacuated chamber, right, I'll put some of the ethanol in it and then I close the system. So I'll close the system essentially because there's no pressure, there's no active force keeping the ethanol in the liquid phase. Then some of those ethanol molecules will break free and become the gaseous phase because there's no pressure forcing it down. Kind of like our liquid propane tank. We can take gas propane, turn it into liquid propane by putting enough pressure on it. But because there's no pressure in this system, nothing is keeping those ethanol molecules in the liquid phase except intermolecular forces. So some of those molecules will go into the gas phase, but eventually it'll stop. Some gas will be formed, some liquid will be left behind, and eventually when the pressure, since some gas particles are going into, molecules are going into the gas phase, our pressure will start to increase in our vessel, and eventually that pressure will stop. All right, so yeah, so molecules begin to vaporize, pressure increases. So vaporize just means liquid to gas. Pressure increases, the molecules, so essentially, eventually, pressure increases and pressure stops changing. So eventually, after we introduce after we introduce our ethanol sample, the pressure will increase, and then eventually that pressure will just stop changing. It'll increase, but it'll like come to what we call an equilibrium pressure, where it stops changing. It's not that gas molecules are no longer being produced. It's actually that the rate at which molecules leave and enter the liquid are equal. That every time a molecule that is a gas particle enters the liquid and becomes a liquid, at the same time a liquid molecule will vaporize and become a gas at the very same time. So you have this gas molecules becoming liquids, liquids becoming gases, and both of those rates are the same. So you see a net change of 0. And so that's why the pressure stops changing. And you will go more into this when you talk about equilibrium in 1220, but that is how you define equilibrium vapor pressure. All right, and every substance at any different temperature has a different equilibrium vapor pressure. So once we get that pressure to stop changing, that equilibrium pressure of the vapor is called its vapor pressure at usually it's at some temperature. Okay, so let's talk about vapor pressure and how that depends on temperature and intermolecular forces. So the vapor pressure that you measure, right? We measure this once the pressure stops changing, we can measure some type of pressure. What that value is dependent on a couple things. One, it's dependent on the temperature of the sample. All right. So it's how fast those molecules are moving. The more kinetic energy we give it, the sample, you can think, okay, the more gas particles we can make because we're putting more energy into the system. If it's hotter, then more molecules are going to escape. The vapor pressure is probably going to be larger. Right? Vapor pressure also depends on strength of the intermolecular forces on that liquid. So all those molecules in the liquid, if they're holding on together really, really tight, it's going to require more energy to get them to go into the gas phase and increase your vapor pressure. Right? What the vapor pressure is not dependent on, and this is kind of a brain buster, is the amount of liquid in the container. As long as there's some liquid in the container, it doesn't matter how much is in there. They will all have the same vapor pressure. So if I have, a container, if these are all closed containers, right? If I have like a tiny bit of liquid, this is my liquid. If I have a bunch of liquid, or if I have a medium amount of liquid, all of these pressures will be the same. Whoops, P vape, that means vapor pressure. All of them will be the same. It doesn't matter because essentially enough gas molecules will leave the liquid to achieve that vapor pressure that's defined at that temperature. All of the pressures will be different. But because all of the volumes of the headspace are different, the amount of molecules will be different. So if you used PV equals nRT here, P will be the same. But because volume is different here, because volume is different here, the number of moles the number of molecules above in this headspace will be different for all of them. But P vape will be the same for all of them. And then the same goes, even the size of the container. So if I had a really big, 5-gallon container of water, right? If I just had a tiny bit of water at the bottom and I close that, that jug of water, right? The vapor pressure inside here will still be the same as all of these other vessels if it's water, right? Or if it's any substance, as long as we're comparing all four different of the same substances. So the vapor pressure inside this container will be the same as all of these as well, right? But the number of moles of gas particles will be different because the volume is different. But P vape stays the same in all four of these vessels. I think that's kind of a misconception that students oftentimes they just miss. If I'm looking at the vapor pressure over the ocean versus the vapor pressure of water over my tea, as long as they're in the same temperature, they in theory should have the same vapor pressure above those two systems, as long as they're one at the same temperature and they're the same substance. Although my tea isn't the same as the ocean, let's just pretend it's just water that we're measuring vapor pressure, but you get the idea. Okay. So the general trend we see with vapor pressure and temperature and intermolecular forces. At high temperature, you will see a higher vapor pressure. That's because we have an increased amount of kinetic energy. More kinetic energy to kick those liquid molecules into the gas phase. All right. Also, if we think about intermolecular forces, if there's more intermolecular forces available in a sample, it will have a lower vapor pressure because you can just think those liquid molecules are hugging one another. They don't want to leave the liquid phase to go into the gas phase. Right? Okay. Holding on to liquid phase. Okay, so let's take a deeper look into vapor pressure. So we talked about how vapor pressure changes. You typically see higher vapor pressures at higher temperatures, and you see lower vapor pressures with stronger intermolecular forces. And so this gives way into different types of vapor pressures given by different types of substances, depending on how much intermolecular forces are available. So here, every substance has its own specific vapor pressure curve. And essentially what a vapor pressure curve is just a graph that shows the relationship between vapor pressure and temperature of a substance. So um, these are a couple vapor pressure curves of different substances. So if I look at water, so here's water, water at room temperature right here, around 70-ish degrees right here. If I had a sample of water in an evacuated flask at 70 degrees, you would probably read a vapor pressure of the container of about I don't know, like 250 torr or millimeters of mercury. Or if you think, okay, the vapor pressure above above your liquid sample of water, your cup of tea or whatever, if my cup of tea is at let's say it's at 90 degrees Celsius. I have like a cup of really hot tea. The vapor pressure, the partial pressure of the water above, or of water vapor above my tea will be about 600 torr above my liquid tea. So one of the things that comes out of these vapor pressure um, curves is the boiling point of different substances. So the boiling point, like if I ask you, okay, what is the boiling point of water? You will tell me, oh, it's 100 degrees Celsius. So the boiling point is the temperature at which a substance boils. So we can also think about boiling in terms of vapor pressure. A liquid will boil when its vapor pressure equals the external pressure on its surface. So essentially what that means is on Earth, when the vapor pressure of a substance becomes 1 atm, or in this case 760 torr, then the solution will begin to boil, or the substance will begin to boil, right? Because that is um, the external pressure on the system, on our sample, is the external atmospheric pressure. All right, and the temperature at which that happens, where we keep increasing the temperature and the vapor pressure increases, right? Once the vapor pressure equals that of 1 atm, whatever temperature that is the boiling point of that substance. So here you can see three or four different substances. We have ether. So at 760 torr, that's where all of these lines are crossed. Essentially, diethyl ether will boil at about 35 degrees Celsius. All right, so just above room temperature, a little hotter than room temperature. And then here we have ethanol will boil at almost 70 degrees Celsius, and then water, as predicted, its vapor pressure equals atmospheric pressure at 100 degrees Celsius. While here, ethylene glycol, it's not even within our scale, but you would predict, okay, if its curve will keep going out like this, so its boiling point is probably very, very high. All right. So essentially, we defined this as the normal boiling point. Normal just means boiling point at 1 atm. ATM being our regular earthly atmosphere, right? So liquid is this temperature, which is vapor pressure is equal to 1 atm, right? And so this explains why, if you've ever baked, one of those like pre-boxed, like pre-mixed cakes or like cupcakes or something, on the package it will say, okay, if the bake time is like 12 to 15 minutes. But if you live in elevated areas, bake it for a little bit longer. It'll say like 17 minutes or something. So why is that? It actually has to do with vapor pressure and deviation from the normal boiling point. So water boils, okay, so at sea level, the pressure of the atmosphere is about 1 atm. Let's say 1.0 atm. So that's here. So water will boil at 100 degrees Celsius at sea level, right? But let's say in Colorado, where the vapor pressure, or sorry, the atmosphere is thinner because miles up above, you're miles above sea level, there's less atmosphere pushing down on you. There's less air up there too, right? So that's why a lot of like athletes go to train up in Colorado, because their lungs are getting used to like being deprived of oxygen essentially before they go to their regular sporting events where the atmosphere is regular and they have like this burst of extra oxygen into their body, right? So in Colorado, the pressure up there is less essentially. So because there's less pressure pushing down on the liquid, it will be easier to boil water. So in Colorado, oh, I didn't capitalize that, but whatever. Water boils below 100 degrees Celsius, slightly below, where it's actually significant. So in Colorado, you'll have to bake your cake for a little bit longer because water is boiling at slightly less than 100 degrees Celsius. Right? And this is another reason that if you've ever cooked with a pressure cooker before. So pressure cookers, I believe they operate under like 15 psi. That's what the gauge I think is on a pressure cooker. So if you're essentially what a pressure cooker is. You're taking a container, you fill it with water, and like your whatever you're cooking, like your chicken or pork or something, you close it up, you seal it up, and all there is just a little gasket on it that can control the pressure. You put it on the heat, right? And you start boiling water. But it's a closed environment, right? It's a closed environment. So essentially the pressure will start to increase in the container until it maintains about like, I believe it's like 15 psi inside the container. So this is extra pressure. So you're pressurizing that water. So since there's this extra pressure available, you are actually increasing the boiling point of water because it's boiling under a pressured environment, and so water will actually boil at an even higher temperature in a pressure cooker, and that's why pressure cookers typically speed up cooking processes. All right, so that's how vapor pressure curves like apply to you directly. All right, so so if we take a look at that curve mathematically, the vapor pressure curve, the relationship between, you'll see that the relationship between vapor pressure and temperature is not linear. All right, so if you look back at these are all curved graphs. It's not like a linear graph. So if we want to inspect it mathematically, we have to use something else. We can't use a linear line. We have to use something else. So let's see what that is. So here's a graph. It shows the vapor pressure curve of ethanol. So you can see here that this is ethanol. Its boiling point will be so at 760, its normal boiling point is around, around 70 degrees Celsius. What this graph shows is actually a logarithmic relationship. All right, so not linear. Okay, it's logarithmic, and it's actually explained by an equation that we call the Clausius-Clapeyron equation. So it is the natural log of pressure, of vapor pressure of a sample, is equal to its negative enthalpy of vaporization over RT plus C, which is a constant. So temperature needs to be in Kelvin. R needs to be in, this is our joules per mole Kelvin, R, mole Kelvin. So this is 8.314 joules per mole Kelvin. And then our delta H of vaporization, this is a value that you can look up in literature values. So just like enthalpy of bonds and stuff, these are typically just like numbers you can look up. Delta H of vaporization, typically you need this to be in joules per mole, but sometimes in a textbook you might see it be in kilojoules per mole. All right, and then pressure typically I believe has to be in ATM. Okay. All right. So this is the Clausius-Clapeyron equation. Again, I have it again, where P is the vapor pressure of the gas at a certain temperature that is in Kelvin. Delta H of vaporization is our enthalpy of vaporization. R is our ideal gas constant, the 8.314 and then our constant. So if you kind of look at this equation, at the L, so we have this natural log value minus delta H, which is just a value you look up, R, which is also just a constant, divided by T, which can change because remember we want to change, temperature and see how does pressure change, plus C, a constant. So you can rearrange this equation into a straight line. Essentially, this is what it becomes. So you have this ln P, that's Y, equals M, which is negative delta H vape over R. X is 1 over T. So I just did some like mathematical arrangement of this quantity. And then plus B or C, which is our constant. So you can see how the Clausius-Clapeyron equation can turn into a straight line. So if we take that linear line that we kind of came up with in that last slide, so right here, right, our linear line, ln of pressure equals negative delta H vap over R times 1 over T, which is our X, plus B, a constant. Now we have a straight line. I like straight lines. They're a lot more straightforward to work with. They're just easier to work with, all right? So now, if we can kind of force that equation into a straight line, we can now see a more direct relationship between pressure and temperature, right? So the Clausius-Clapeyron equation relates pressure and temperature. So if we plot the ln, or the natural log of a vapor pressure, remember this is vapor pressure, versus 1 over T, 1 over the temperature must be in Kelvin, all right? Then we get this relationship. For one type of substance, we should get a straight line, right? And so the meaning of the straight line comes from our Clausius-Clapeyron equation. The slope of our straight line, as long as we plot, ln of p versus 1 over t, so y versus x, we should get that the slope is equal to negative delta H vap over R, where R is 8.314 joules per mole Kelvin. This is great. So we could take a sample, put it in a closed container, measure a bunch of vapor pressures at a bunch of different temperatures, and if we plot it, we can get a thermodynamic quantity from that. Isn't that great? No? I think so. All right. So yeah, we can determine delta H vape of a certain liquid sample from this, where delta H vape equals the slope that you get from relating ln of p versus 1 over t times r. You will do this in like your first week in Chem 1220. All right. And so we don't have to do this experimentally and make a whole graph and do a whole bunch of points, get a slope of a line, a straight line. You can also use the Clausius-Clapeyron equation with just 2 points, because remember, 2 points always make a line. So we can use the Clausius-Clapeyron equation to relate 2 different points. So here's just a proof of how you do it. I will never have to make you do this proof. You just need to know this equation, which I will give you. All right. So how this proof works is I take the Clausius-Clapeyron equation, just like the regular one. All right. And what we're doing is, our goal here is to get delta H vape of a substance by relating 2 different pressure volume data points. That's it. So how this works is, I am going to take 2 different pressure temperature data points. So I'm going to set up 2 Clausius-Clapeyron equation. So one will be the first data point, the first pressure equals negative delta H vape over R, 1 over T1, so the temperature that corresponds with the first pressure. And then I'll have another iteration of the Clausius-Clapeyron equation where this is now the second data point. All right, so I have 2 pressure volume data points. Essentially, we're just going to look at 2 data points. We don't have to make the whole line. We can just do 2 data points. All right, so 1 data point 1 set versus the second set of data points. So if you use your logarithm rules, you can put these 2 equations together by using logarithm rules. All right, and so you get that the natural log of pressure 2 minus natural log of pressure 1 equals negative delta H vape over R, 1 over T2 minus 1 over T1. And so you can rearrange these natural logs into ln of P2 over P1 equals, now the negative goes away because I think we flipped something. We flipped these 2, so the negative sign goes away. 1 over T1 minus 1 over T2. So this is our new Clausius-Clapeyron equation. So this is our Clausius-Clapeyron equation for 2 points of the graph. So you need a pressure and temperature data point, 2 of them. You need 2 sets of those. All right. So we've talked about delta H vap, and well, we kind of ignored this. We've been talking about vapor pressure. So we're relating 2 different vapor pressures at 2 different temperatures, and it's all dependent on its delta H vape. What is that? Well, delta H, or enthalpy of vaporization, has to do with phase changes and the energy it requires to change phases. How much energy does it require to turn a liquid into a gas? How much energy does it take to turn a liquid into a solid? These are all enthalpy values. So here's just a bunch of phase changes that you and I are probably familiar with, but maybe not so much familiar with whether these reactions are exothermic or endothermic. So remember, exothermic means that energy is released. Usually there's a negative sign associated with exothermic. So a negative energy to indicate the direction that energy is leaving the system. Well, endothermic means that energy is added to system, or the system gains energy. So maybe released by system. I'll say that. And typically there's a positive energy that corresponds with an endothermic process. So all of these different processes going from a liquid to a gas to a solid. Okay, so we probably know what these terms are. To go from a liquid to a gas, typically we call that vaporization. That's when a substance boils, going from a liquid to a gas. Well, when a gas goes to a liquid, that's called condensation. So what this graph is showing is that in order to go from a liquid to a gas, we need to add energy to the sample, to the system. So if you have a 100-degree container pot of water, that's a liquid. It's going to take some extra energy to turn that 100-degree vat of water to 100-degree vat of gaseous vapor water. You have to add energy into the system to just turn a liquid into a gas, even if it's at the same temperature. Right? I can have water liquid that is 100 degrees Celsius, but to turn that liquid into a gas, you need a little bit extra energy in order for that vaporization to occur. And that process, in this case, is endothermic because it requires energy to turn a liquid to a gas. But then, if you, and actually, okay, so something that, to relate this to something in real life. So if I sweat, I'm sweating, right? It cools you down, right? Sweating cools you down because liquid sweat, so like water essentially, will coat your body, right? So you have this liquid water. And as sweat evaporates, you cool down. Because in order to turn that liquid into a gas, it requires energy. Where is that energy coming from? It's coming from the heat in your body. So essentially, some of the heat energy in your body is entering your sweat, liquid sweat, to turn it into a gas. So then heat is removed from your body as you sweat, and through the process of vaporizing a liquid sweat into a gas. Right? Okay, so that is indication that vaporization is an endothermic process. On the flip side, if you want to turn a gas into a liquid, it's typically called condensation, and that's an exothermic process. Gas molecules, they're moving super fast. In a liquid phase, they're not moving as fast. They're all condensed phase. They're not moving as much. Maybe they're vibrating, but they're next to each other. Gases, they move up all around. There's a bunch of kinetic energy in a gas. So when you're going from like this crazy molecules flying everywhere gas sample to a more tame liquid sample, that extra energy has to come from somewhere, right? So from undergoing condensation, that extra energy from a gas is released into the surroundings. And so that's an exothermic process. So think about the different kinetic energies of these systems, and you can see energy of the system, right? Solids have the least amount of kinetic energy. They're moving. So molecules have the least amount of kinetic energy, all right? Molecules have most amount of kinetic energy for a gas. So essentially, that gas is going to lose all of its kinetic energy through the process of condensation to become a liquid. Same thing with going between a liquid and a solid. All right, we know going from a liquid to a solid is called freezing. So if I have liquid water at 0 degrees Celsius, in order to freeze it, to make it become a solid. So essentially, in a liquid, all those water molecules, they're vibrating, they're moving past one another. They're at 0 degrees, and they start slowing down, slowing down, slowing down. At some point, those molecules stop moving as fast and slipping past each other, and that liquid water becomes solid water in the process of freezing. But that kinetic energy from that liquid sample has to go somewhere. Right? And so that is what we call the enthalpy of fusion or freezing, which I think I talk about in the next slide. Yeah. That is associated with freezing. All right. Same thing with going from a solid to a liquid. To go from 0 degree ice to 0 degree water, it requires you to put a little bit of energy into that to get the molecules to start to slip past one another, enough kinetic energy for those molecules to slip past one another to become a liquid phase. So you see here, so we kind of took care of the liquid and gas phase transition, and we took care of this liquid and solid phase transition, which I think most people are used to. They know liquid to gas, liquid to solid. But then we also have sublimation, solid to gas, gas to solid. So an example of a substance that sublimates is solid CO2 or dry ice. All right, and so you can see that the arrow for sublimation is just the addition of condensation and freezing, these two arrows. All right, so what's really important about this slide is to know where energy is going into the system or out of the system. All right, so kinetic energy of your sample is what is defining whether a process is exo or endothermic. All right, so sample, so if we go up, so sample gains kinetic energy. So oftentimes the processes are endothermic. So endothermic, all of the up arrows are endothermic, while these down arrows, sample loses kinetic energy. So these are exothermic processes. So that extra kinetic energy has to go somewhere, and it usually leaves the system and enters the surroundings. Okay, so yeah, think about change of kinetic energy to determine sign of the process. Great. So so all of those arrows have a name associated with them. It's really important because with all of these arrows, they are all the same value, but you have to come up with a sign. So with one of those arrows, heat of fusion is associated with the liquid and solid transition. So going from a liquid to a solid and a solid to a liquid. It's up to you to figure out what that sign is. So enthalpy of heat or enthalpy of fusion, or heat of fusion, sorry, usually defined as delta H FUS, is the energy required to convert 1 mole of solid at its melting point to a liquid. And the negative of the heat of fusion will be the amount of energy released, turning a liquid to a solid. All right. Next is enthalpy of vaporization. We've been talking about this. So this is liquid going to a gas or gas going to a liquid. I'm going to flip this. So solid to liquid, liquid to solid. Okay. So enthalpy of vaporization is defined as energy required to convert a mole of liquid at its boiling point to a gas or vapor. So delta H is usually a lot larger than delta H of fusion because in vaporization you have to separate your molecules much further to produce a gas than turning a solid sample to a liquid sample, right? So a solid sample to a liquid sample, you're only breaking some intermolecular bonds or intermolecular forces, while in vaporization you have to break all of the IMFs and the molecules are becoming much further apart. So yeah, delta H vape is usually much larger than delta H fusion. Okay. And then typically the stronger intermolecular forces, the larger delta H vape will be. That makes sense. The more intermolecular forces keeping those molecules together, the more energy it will take to separate them to become a gas. And then finally, the last point, delta H, or sorry, the enthalpy of sublimation, defined as the energy required to convert 1 mole of solid to 1 mole of gas. Whoops, gas solid. Said one thing, wrote another. Solid going to gas. And usually your delta H of sublimation is just the addition of your fusion and vaporization enthalpies as shown by this graph. So essentially, if we wrote what these are, so this liquid gas transition is defined by our delta H vaporization, right? I'm going to put it over here because vaporization is a positive value. So it's the positive version of delta H vape. Our condensation is our negative delta H vape. All right, melting to melt the solid, that is our delta H of fusion. That's a positive value. It requires energy to melt a solid to turn a solid into a liquid. And then freezing is negative delta H fusion. And then finally, sublimation to go from a solid to a gas, that is our positive delta H sub. And then deposition is minus delta H sub, sublimation. All right, okay. So this graph kind of summarizes everything in this slide. Okay, so we can compare some different phase changes for different substances and kind of think of what IMFs are present in all of these. So I'll just tell you that butane only has London dispersion forces. Diethyl ether has London dispersion and dipole. Water has all three, so London dispersion forces, dipole-dipole, and hydrogen bonding. And then finally, Mercury has London dispersion forces, and they're very, very strong because Mercury is a very heavy element. So very heavy element. So London dispersion forces are very strong in Mercury. All right. So you can see essentially with this whole graph that going from left to right, that our total IMFs are increasing going from left to right. So you can kind of see that if we compare the like heats of vaporization, it increases going from low amount of IMFs to high amount of IMFs. All of them are increasing, right? And then you can also see that for most of these, our delta H of sublimation is equal to our delta H of fusion plus your delta H of vaporization for the majority of them. I think for all of them. 23 plus 58, yeah, that works. Yep, that works. Yep, so for all of them, it follows that the green heat of sublimation is equal to the heat of vaporization and the heat of fusion, the addition of these two boxes. All right, so let's put all of our phase change knowledge into a different type of diagram. So if you take all those phase changes that we just talked about and put that into a diagram, we can come up with what we call a phase diagram of a particular substance. So what this diagram shows is it shows you the stable state of matter, so solid, liquid, gas, of a certain substance at different pressures and temperatures. And that's what these colored boxes are. It also shows you the places where equilibria exist between phases. So what I mean by equilibria it's what I mean by phase change. So like boiling water is a phase change between a liquid and a gas phase. So when you boil water, both the liquid and gas phases are present at the same time until you've boiled all the water off. That is what we mean by equilibria. Both of those, the liquid and the gas, will exist at the same time at 100 degrees Celsius until all of the liquid is boiled off, and then finally that gas can increase in temperature. Okay, so this phase diagram is not for water, it's just for like some other generic substance. So what I want you to see is we have different regions where each of the different phases are most dominant and the most stable. So you can see at very high pressures, you apply enough pressure to it, squeeze molecules together, you have a solid. Right? At really, really high temperatures, you've given the sample enough kinetic energy, all those molecules are moving around, you have a gas at very high temperatures, right? So temperature is increasing that way, pressure is increasing that way. And then somewhere in the middle you have a liquid, right? So let's think about this. So let's think about this. What do I want to talk about next? Let's go here. So yeah, so each of these colored regions are conditions where only one phase is stable. So here, like for this particular substance, you have solids at high pressure and low temperature. Gases will be the most solid phase at a high temperature and low pressure. Right? And then finally, liquids are just somewhere in the middle, like an intermediate pressure and temperature. All right, so those are those regions of the phase diagram. So then the lines on the phase diagram indicate the equilibria, or remember I won't do black, our phase changes. All right, so these are the solid lines here. So this blue line, so if I have a liquid, so I'm at this particular pressure and temperature. If I decrease my temperature, and eventually, so my samples at this particular temperature, I stay at the same pressure, I eventually decrease my temperature, and eventually I'll hit a certain temperature at which the phase change starts to occur. All right, so I hit that line. So at that line, I have this equilibria, our solid liquid equilibria. All of the, or equilibrium, because that's singular, equilibria is plural. So essentially, so my liquid sample, it will stay at this temperature until all of the liquid has now turned into a solid. That's called freezing, right? And then finally, once all of the liquid is now a solid, then the equilibrium is done. Then I can continue to cool down my solid sample. So at this point right here on this line, both the liquid and solid exist at the same time, only at that pressure, at that temperature. Okay, so that is an example of like the liquid solid transition. So what if I go back, let's go back to our starting point. So this liquid, what if we decrease the pressure instead? So essentially we're going to evacuate all of the atmosphere out of a vessel. So we're going to make it like a vacuum. And so if it's a vacuum, then there's no external pressure forcing the liquid to be in a liquid state. All right. So slowly we decrease our pressure, right, to a certain point at a certain temperature. Eventually, it will become a gas. Or you can think about it this way. How about let's think about it this way. Let's start as a gas. So we are at, a certain temperature and a low pressure. Let's think of our propane gas, right? So in order to fill a propane gas tank, we have to put the gas under extreme amount of pressure. So eventually, we have like, room temperature, atmospheric pressure. Okay, so then we start to apply a lot of pressure to the gas. Maybe we're squeezing its volume to make it smaller. As you squeeze that and increase the pressure, right? You're going to turn that gas into a liquid. And once all of the gas has turned into a liquid, and then now you have a liquid essentially instead of a gas, then your pressure will start to change again. So at this point where we have both a gas and liquid present, pressure does not change until all converted to a liquid. All right. So essentially, anytime you cross one of these lines, typically you're moving in either, a horizontal line fashion by changing your temperature, or you're moving up and down, changing your pressure. Whenever you move across one of these lines, you will melt, like you'll do one of these transitions, these phase changes, either melting, freezing, vaporization, condensation. So that gas to liquid was condensation, or gas to solid, sublimation, or deposition. All right. So what else can we inspect on these phase diagrams? So other things that are present on this phase diagram are the triple point and the critical point. So these are two different points. At the triple point, just like, oh, this should be bolded. The triple point, just like in the name suggests, all three phases exist in equilibrium. It's only in one point. It's at a certain pressure and temperature. Only at one point. All three phases. Ooh, weird. Three phases will exist at the same time at the triple point. So in this graph, it's right here. It's where all three of the colors intersect. Okay? So all three phases will be there at the same time. You might wonder what that looks like. So once I accidentally made conditions for the triple point of, I think, cyclohexane. And what it looks like is water. So cyclohexane is just like a colorless liquid, so it looked like water. So it was boiling, and then all of a sudden it would like freeze. It would like seize and like freeze, and then it would like melt, and then it would like start boiling again. So it was like just doing all of that, like freezing and then like melting, then starting to boil again, like all at the same time. Yeah. Okay. So that is the triple point. So then we have this other point here that I want you to look at, and this is the critical point. So at a certain, typically it's really high temperatures and high pressures, we have a critical point. Essentially, it's the vaporization line, the red line, right, where vaporization and condensation occur. The line just ends, and it ends at the the critical point. So any temperature or pressure above this point, liquids and vapor are indistinguishable from one another. And so in this region, we have a supercritical fluid. Supercritical fluids are important in like the new age industrial revolution that we're kind of in. Supercritical fluids can allow us to get more extract more substances out of like natural products. It can allow us to do new reactions that we've never done before. Supercritical fluids are pretty important in industry. So this is important. So it's important to us, as a society. But what it means is that essentially it's a liquid and vapor at the same time. So we kind of have both properties of gases and liquids at the same time. Liquids are good solvents typically. Gases move really fast and there's a lot of energy available. So combine those together, you get really great reactivity in supercritical fluids. So essentially, a little bit more about this temperature. At this critical temperature or your critical point, um, a vapor cannot be liquefied by applying pressure any longer. So any temperature, like here, any temperature in like this box, right? If you're anywhere above this temperature, you cannot liquefy something by applying pressure, like our propane example. So if I took propane and like heated it up like a ton, and then I wanted to liquefy it, I might not be able to do it if I'm above the critical point. But thankfully, at room temperature, right where we store our propane tanks, we can still, we're below the critical point temperature, and we can still liquefy propane to use in our propane tanks. Great. Okay. So here's a relationship I want you to memorize. Stronger intermolecular forces means a higher critical point. Higher meaning like it's like higher. I think I have an example here. Mm, no, no, I think it's in the next slide. But anyway, so just a side note, let's think about boiling points and melting points on these phase diagrams. So you might ask yourself, okay, where is the normal meaning, remember 1 atm on Earth, melting point and normal boiling point. So you need to find the phase transition line, or so the solid line, at the 1 atm mark. So your normal melting point is the solid liquid, our solid line. So what color is melting? Blue line, solid blue line. At the 1 atm line. Do I have that here? No. I don't have this to scale, but like let's pretend like right here is 1 atm, right? So everything along this line right here will be our liquid to solid. So this is our melting point, right? And then our normal boiling point is where the vapor pressure of the liquid is 1 atm. So that would be right here. And it's also, the liquid gas. Yeah, so right here, liquid vapor sample is 1 atm, the sample boils, so it's our liquid gas solid line, but it has to be at 1 atm because this is our normal 1 atmosphere gas, liquid gas transition. So it would be right here between the red line. So it's the solid red line, but it has to cross 1 atm. Okay. But maybe, I could ask you, okay, the atmosphere on the moon is like, I don't know, 10% of that of the Earth. What is the melting point and boiling point of water on the moon? So you would choose a different pressure, whatever corresponds to what it is on the moon. It would be somewhere down here. And so all the values you would get would be somewhere down here. Okay. Okay. So let's keep going. Okay. So here's the phase diagram of water. So water has pretty high intermolecular forces because there are hydrogen bonding available. So note that you have a really high critical point, right? So this is a very high critical point because we have high IMFs. Okay. Water has strong intermolecular forces, hydrogen bonding. So you can see here, so we can find the normal melting point and normal boiling point. Again, that means at 1 atm. So what we do is we just find 1 atm. So there's one of our points, and there's another one of our points. So this point is our melting point because we're going from a solid line, or sorry, the solid to the liquid phase. And then here between liquid and gas, this is our boiling point. And so you can see what temperature that actually corresponds with. So here it's around 0. My lines aren't that straight. And yeah, it's about 100. 100 and 0, right? So hopefully, use your intuition. If you check this out as you do it yourself at home, you can see that it does check out that the melting point is 0 degrees Celsius and your boiling point is 100 degrees Celsius. Okay, so one other thing about water that is kind of interesting that you might not have noticed with all the other phase diagrams that we've seen. So this phase diagram for water is slightly unusual because the slope of this blue line, so the slope of the blue line is negative. It goes this way. So in this diagram, it goes this way, right? And I think so this one, it's like a positive slope, right? But in water, it is negative. It kind of flips back the other way. So this is relevant to us Because water is one of the only substances that become less dense as it freezes. So ice floats. Almost literally all other substances actually get more dense when it freezes. But water is special in that it actually gets less dense as it freezes. So the solid form is less dense. So solid is less dense than the liquid. That's why ice floats. This phenomena is not seen in any other substances. So it's really kind of like a miracle that water behaves this way because it explains a lot of this. We see this phenomena in a lot of places. It's why icebergs float. It's why ice floats in your drinks. It's why if you put water in a glass container in your freezer, it'll explode. It'll break the glass. Things like that. So it's quite amazing that water is pretty much the only substance that will become less dense as it freezes. So so yeah. Oh, I already did this. We already did this. Use normal melting point and boiling point of water. Use intuition to make sure it makes sense. Okay, sorry, I put it twice. Okay, all right. So let's look at one other example, carbon dioxide. So one area, we've been talking a lot about the like solid liquid transition or phase change, liquid gas phase change. What we haven't talked about is our solid gas phase change, so sublimation. All right. So let's do the same type of question. Let's find the normal boiling point and normal melting point for CO2 in this graph. So I have it right here. Find it. Okay. So what you should do. So normal means 1 atm. So you go to find 1 atm and you draw a line, right? And you find the solid lines. But well, crap. The solid liquid transition's up here. It's not down here. Our liquid gas transition is up here. It's not down here at 1 atm. Well, crap. So you cannot. So this was a trick question. You can't find them. So yeah, having trouble finding them. It's because the normal boiling point and melting point for CO2 does not exist. Normal, again, meaning at 1 atm. Think about dry ice. Have you ever seen dry ice or bought dry ice? Dry ice, if you buy it, you have a solid block of dry ice, and then eventually it disappears because it becomes a gas and it leaves nothing behind. All right, because dry ice is solid CO2. So this makes sense. At 1 atm on Earth, solid CO2 will become a gas anywhere above negative 100 degrees Celsius, which is pretty dang cold. So, we live up here in the 22 degrees Celsius realm, right? So all of that solid dry ice will sublimate and turn from a solid to a gas. So this is our sublimation. So that explains why dry ice behaves the way it does. Okay, well, what about its melting point and boiling point? Well, where are they? What does this mean? It means that carbon dioxide can't exist in the liquid state at pressures below the triple point, essentially. So we have to increase the pressure of our surroundings in order to make liquid CO2, unfortunately. So we can never have liquid CO2 just in like earthly conditions out in the open. We have to put the system, a CO2 sample, under a ton of pressure, almost 5 atms of pressure in order to get it to become a liquid. And then we can change the temperature and go from solid to liquid to gas. Right? Yeah. So from this graph, you should see that we cannot have liquid CO2 at 1 atm, or that you cannot have a normal boiling point and normal melting point because the liquid phase does not exist below 5 atm. Okay, so I'll just summarize those. Well, hopefully on your side of things, you can summarize all of the different properties and properties. How does intermolecular forces change these different physical properties? So as IMFs increase, how do these change? So think about viscosity, surface tension, vapor pressure, enthalpy of vaporization. Oh, what else? We have critical point. Right? That's one too. All right. So how do all of these change as IMFs increase? So from here on out, in all chemistry related classes and biological classes, you're probably going to be thinking about intermolecular forces. So, take a step, like take a second when you see a question, and see what compounds are present in your sample, how intermolecular forces can change the different physical properties that you might be measuring and observing.